And
Thank you.
Willard, yes.
Thank you, Professor.
Yeah. Okay, for you guys, for you, let me see, for Martin. For Martin, it just gives me remove the permission. So it seems that I already gave you. Fred, now you should be able to. For you, Willard, it just gives me remove permission to record the files. So you should be
No,
able
I
to.
already have it. Thank
All
you.
right, perfect. So is there anyone else? Fred, you should be able now. And so are you, Willard. Okay. So it seems that everybody fine. I'm going to record it myself, share my screen with you guys. And here we are. Let me go to, you're in session 2, chapter 2, session 2. And let me see. Oh, not this one. All right. All righty. Did we talk about the method of heat transfer? I don't think so. Did we talk about conduction, convection, and radiation? No, I don't think so. Okay. So say we want to talk about different methods of heat transfer. Of course, this is not a transfer course, so I'm going to just explain this briefly because in heat transfer, the conduction alone is 3-4 chapters. Convection, that is like several chapters, and radiation 2-3 chapters. So here, we just want to review them in a couple of slides. The heat can be transferred to or from a system through 3 mechanism, method: conduction, convection, and radiation. Because we previously talked about energy balance equation. So if this is a system, the total energy transfer into the system minus the total energy transfer out of the system, the difference is change of energy of the system. And we talk about the right side of equation. This is just a quick review. The change of energy of the system, I'm talking about delta E of the system, you can break it down into change in kinetic energy plus change in potential energy plus change in internal energy of the system. But the left side, which is energy transfer into or out of the system, it can be through heat transfer into or out of the system. It can be through work transfer into or out of the system. And it can also be through heat transfer into or out of the system. So we start with heat, which can be transferred into or out of the system through conduction, convection, and radiation. And, conduction is where heat is being transferred from, more energetic particles to less energetic particles. And in convection, it is being transferred between a surface of solid and adjacent fluid. We're going to talk about that. And in radiation, just through electromagnetic waves. And, if, for example, you consider a wall and there is temperature gradient, meaning temperature is not uniformly distributed, and the area of the large wall is A, and it's made of some material, and, conduction coefficient for that, which depends on the material. So for wood, is different than glass, is different than metal. So that is conduction coefficient, K. So heat, the rate of heat transfer, that means rate, Q for heat. So rate of heat transfer through conduction. So subscript shows its conduction. Rate of heat transfer through conduction can be calculated using Fourier's law of heat conduction, which is minus Ka, derivative of temperature respect to X. So we've assumed that it is 1D, and temperature just changes with one dimension within the wall. For example, if this is the thickness of the wall and you take this as x-axis, which is perpendicular to the wall, So we are looking at the thickness of the wall, and x-axis is just perpendicular to the wall, temperature is function of x. X is in the direction of the thickness, and there is the temperature variation within the wall, and temperature is function of x, just 1D. If you take derivative of temperature respect to x, multiply by area of the wall, multiply by conduction coefficient, that that is for coefficient that is depends on the material that wall is made of. Then that gives you rate of heat transfer. By the way, we put a minus sign here because we want rate of heat transfer to be positive. And if a temperature, if x-axis direction for positive x is this way, from left to right, and with increasing x, temperature drops within the wall, then if dx positive, it means dt negative. If this is the direction for heat transfer from left to right, and here is the direction for positive x from left to right, then we know heat is always being transferred from higher temperatures to lower temperatures. So in the positive x direction, temperature drops. So if dx is positive, dt is negative. If you go in positive x direction, temperature drops, so dt negative. So derivative of temperature respect to x is negative, a is positive, k is positive. We put a minus sign here to come up with a positive rate for heat conduction. So as you see, rate of heat transfer is directly proportional to temperature gradient within the wall. And then we get to, that is called, by the way, Fourier's law of heat conduction. Then we get to convection. For convection, there is natural convection, there is forced convection, which can be grouped into internal forced convection and external forced convection. For natural convection is where, for example, there's a table and there's a solid with a surface, and it is in contact with fluid like air. And then if you assume that the surface temperature of the table or surface temperature of the solid is higher than temperature of the fluid, adjacent fluid, it can be the other way too. The only thing that changes is just direction of heat transfer. Heat always is being transferred from higher temperature to lower temperature. So heat is being transferred from, let's say, table to the air, and adjacent fluid becomes warmer and becomes lighter, and it goes up, and it will be replaced with heavier, colder fluid, right? And that creates a bulk motion within the fluid. That is called natural convection. Because fluid doesn't have a velocity, but there is a bulk motion within the fluid due to fluid getting warmer. Fluid adjacent to the surface of the solid becomes warmer and warmer and goes up, and it will be replaced with heavier, colder fluid. So that's natural convection. And there is forced convection when fluid itself has velocity. And by the way, that can increase the rate of heat transfer by convection. And with forced convection, there is internal forced convection. For example, when we are talking about fluid inside the pipe, oil inside the pipe, or air inside the pipe. That is an example from forced internal, convection. And for as an example for external convection, when there is a fluid like vein passing a surface, passing a plate. So that is an example for external forced convection. So there are three type of convection, forced convection, natural convection, forced convection can be grouped into external forced convection and internal forced convection. If you assume that, for example, this is the surface of the solid, which is in contact with fluid, and the surface of the solid has a temperature of Ts, S for the surface, T for temperature of the surface. And the surface that is in contact with the fluid has an area A, and if you assume that the temperature of the solid is higher than temperature of the fluid and TF for temperature of the fluid, it can be the other way too, to just change the direction of heat transfer. Then heat is being transferred from, in this case, if TS is higher than TF, from surface to fluid, right? So that is direction for heat transfer, and Q dot shows rate of heat transfer, and that is by convection. And the rate of heat transfer by convection, rate of Q for heat, dot for rate of heat transfer by convection, that is heat transfer per unit of time. It can be calculated using this formula, HATS minus TF. H is convection coefficient, convection heat transfer coefficient, or convection coefficient. A is area of the surface. Oh, sorry, A is area, yes, of the surface, which is in contact with the fluid, as you see. And TS is temperature of the surface, and TF is temperature of the fluid. And but temperature of the fluid, which is far away from the surface, is not under the influence of the surface, because as the fluid, pass over the surface, it can form a temperature. I mean, we have velocity boundary layer and we have temperature boundary layer. But when we say TF, we are referring to fluid temperature, which is far away from the surface. And the H that you see here, convection coefficient, doesn't just depends on fluid. It's not one of the property of the fluid. It's not like, property of the fluid and you can get it from the table. There are many factors affecting value of H. And one of them, in fact, is fluid itself. And some fluid properties like density of the fluid, viscosity of the fluid, right? But there are other factors like velocity of the fluid can affect value of H. Sometimes, we increase the velocity of the fluid by using fan in order to increase rate of heat transfer by convection. We want to increase rate of heat transfer by convection. So do not think that H is one of the one of the property of the fluid. Fluid itself is one of the factors, and fluid properties are some factors affecting H, but that's not all. There are other factors that will affect value of H as well, all right? And then the third method is radiation. By the way, is there any question I forgot to ask you? I'm taking questions if there is any before I get to radiation. Any question you may have? All right. So for radiation, say any body which has temperature greater than absolute zero will emit radiation. So just for the temperature, so anybody in the world, anything in the world with the temperature Ts, with the surface temperature Ts, greater than absolute zero, can emit radiation. Okay, so how do you calculate emitted radiation? For real surface, I'm going to explain in the next slide, but for the maximum, let's explain it this way. If the surface has temperature equal to Ts, if Ts is greater than absolute zero, that body, that surface can emit radiation. The maximum, listen, the maximum emitted radiation, that is a rate of heat transfer, rate of emitted radiation, basically, and that's a maximum. The maximum emitted radiation from a body with surface temperature Ts is sigma ATS to the power of 4. What is sigma? That is a Boltzmann constant, and that is equal to 5.67, 10 to the power of minus 8. So that's 5.67, 10 to the power of minus 8. And the unit would be, because the unit of this, it's energy, right? Per unit of time, it's rate of heat transfer. Heat is energy. So it's energy per unit of time is watt. That has the same unit as power. So in SI system is watt. And that is for sigma, it's like Q dot divided by A, and then divided by TS to the power of 4. So watt is the unit for rate of heat transfer, and the meter square is unit for area, and Kelvin is the unit of temperature. I'm talking about SI system. So in SI system, the unit for Stefan Boltzmann constant, I'm talking about this constant sigma, is watt divided by meter square divided by Kelvin to the power of 4. Here we are. So that is called Stefan Boltzmann constant. That is the area that has surface temperature Ts, area of the body. That is the temperature of the surface of the body, Ts, S for surface, temperature of the surface of the body. And it has to be expressed in terms of Kelvin or Rankine. It is absolute temperature. Do not use Celsius or Fahrenheit. It is absolute temperature. So it has to be expressed in Kelvin or Rankine. So any body in the world with a surface temperature greater than absolute 0, if Ts is greater than absolute 0, it can emit radiation. And the maximum rate of heat transfer through, emission through, that's maximum emitted radiation, rate of emitted radiation, can be calculated using this formula, sigma A Ts to the power of 4. When sigma is a Stefan Boltzmann constant, here you are, and A is area of the surface, area of the body, right? Area of the body, and Ts is surface temperature of the body. So Ts surface temperature of the body, A area of the body is sigma Stefan Boltzmann, and that is the maximum that a surface or a body with a surface temperature Ts can emit radiation. That is the maximum rate of heat, emitted heat. Okay, and that is maximum can only it is only for black body. Only black body has the maximum emitted radiation, and we're going to see the definition for black body. Black body basically absorb all the radiation that it receives. Yes. Do you have a question, man?
Yeah, I just want to ask. So I'm just kind of confused. So for the A, you said it is the area of the body, not the surface area, right?
See, yes. See, there is a body, right? For example, a body can be you and me, or the table, all right, or the ceiling, or the blackboard. So that body has a area, right? So that is the area of the body which has a surface temperature equal to Ts. Ts is surface temperature, and that's the area of the body.
Okay,
all right.
cool. Thank you.
And yeah, so you use this formula in order to calculate the maximum emitted radiation, and that's rate of emitted radiation. That is the maximum rate of emitted radiation, because, as you know, every body with a surface temperature Ts being greater than absolute 0, it can emit radiation to the rest of the world. You are emitting radiation, table is emitting radiation, ceiling is emitting, everything with a surface temperature greater than absolute 0 is emitting radiation. That's a maximum it can emit, rate of emitted radiation, maximum rate of emitted radiation for a body with a surface temperature Ts and area A. That is the area surface, okay? And the maximum can only occur for black body. For real surface, it is a fraction of that. So for every real surface, the emitted radiation is a fraction of that maximum. Because maximum is this. sigma ATS to the power of 4, sigma is the von Boltzmann constant, area of the surface temperature, TS. And it has to express in absolute, all right? Which is ranking in English system or British system, and it's, Kelvin in a size system, international system, all right? So for real surface, the formula would be this. Rate of emitted radiation would be epsilon sigma ATS to the power of 4. So we multiply that maximum by epsilon. And as you know, epsilon is less than 1. It can be anywhere between 0 and 1 for black body, of course, is 1 because they have the maximum. With the same temperature as anything else, they have the maximum rate of emitted radiation in black body. But any other surface, they cannot reach that maximum. It's a fraction of that maximum, okay, with the same surface temperature and the same air. So that is Q dot is rate of emitted radiation. So how do you read it? Rate of emitted radiation, right? And epsilon here is called emissivity of the surface. It is one of the properties of the surface, and there are tables that you can get the emissivity from that. So that depends on the material. So emissivity of the surface. And by the way, here on the note, I mentioned that every surface or every body with the surface temperature Ts, which is greater than absolute 0 temperature, it can emit radiation. And here we are. That's how you calculate it. And, that is the emitted radiation just due to the temperature. So everything in the world with Ts greater than absolute 0, they emit radiation to the rest of the world. And by the way, any surface, receive radiation from the rest of the world. So we define Q dot incidence. That is rate of radiation incident on surface. So let's go to the next slide. I'm going to go back here. See if this is a surface, right? From the rest of the world, if this surface, for example, is board, black board, it receives radiation from you, from me, from floor, from ceiling, from the walls, from everything. So there is incident radiation on each surface. So that is rate of incident radiation on the surface, right? And also this surface, because of this temperature, it emits radiation, Q dot emit, right? And it is epsilon sigma ATS to the power of 4. A is area, sigma is the von Boltzmann constant, epsilon is emissivity of the surface, Ts is surface temperature, expressing absolute. So due to the temperature, this surface emits some radiation to the rest of the world, and from the rest of the world, there are incident radiation on this surface. Part of incident radiation will be absorbed. Body will absorb that radiation. Part of it will be reflected. A fraction of it will be reflected. Rho is reflectivity coefficient. You multiply by Q dot, and part of it will be, a fraction of it will be reflected, will be back to the rest of the world. Part of it will be absorbed by the body, and part of it will be transmitted through the body, right? The part that will be absorbed is alpha, which is called absorptivity, multiplied by Q dot incidence. And for black body, that alpha is 1. So it means black body absorbs everything it receives. And there is no, the reflected emitted radiation in the black body would be 0. The part that it transmits through would be 0. Just everything will be absorbed, and alpha is 1 in black body. For anything else, alpha is somewhere between 0 and 1, right? So that's that. And by the way, if you consider a small surface, a body with a small surface, like you and me in the world, so a body with a small surface, and the surface of the body is A, like you or me, and the surface temperature is Ts, and emissivity of the surface is epsilon, okay? And, it is surrounded by a large, surface. like, atmosphere. And then, they are separated by gas, right? Then, the net rate of heat transfer by radiation, because this body has some emission because of surface temperature, and then it received some incident radiation, and part of it will be absorbed. So considering everything, the net heat exchange between these two, the net rate of heat transfer by radiation to or from body, it depends. If it's to, it's gain. If it's from, it's loss, right? But that is a rate of heat transfer by radiation to, or it can be to or from body. It depends if you come up with a positive or negative value here. The net rate of heat transfer by radiation to body would be epsilon sigma A Ts4 minus T surrounding 4. So the temperature of the surrounding, okay, and Ts is the surface temperature of the body. And this is a small body enclosed by a large body, and they are separated by gas. And A is area of this small body, like you, me. Sigma is a Boltzmann constant, and epsilon is emissivity of the body. So this is for the body, emissivity of the body, area of the body, a Boltzmann constant, surface temperature of the body, and temperature of the surrounding. And that is rate of heat transfer. Q dot is rate of heat transfer by radiation to or from body. To body, basically. But if you come up with a negative value, that is from body. So it can be heat gain or heat loss, but that is net. Okay, that is net. Is there any question before I get to the second part of E in minus E out? Because E in and E out, E in means heat transfer to the system. The system can be piston cylinder. The system can be pump and fluid inside it, or turbine fluid inside it. So, and heat transfer into or heat transfer out of the system. You can break it into these components. First, I mean energy. Sorry, I misspoke. E, energy transfer into or out of the system. It can be through heat that we just explained. It can be through work that we want to talk about. It can be through maths if the system is open. Okay, so now we want to talk about work transfer into or out of the system. So if work is done on the system, that work will be added to the system. If the system does work on the surrounding, that work is out of the system, and that can decrease the total energy of the system, right? So work can be done on the system, or the system can do work on the surrounding. By the way, anything outside the system is called surrounding. For example, if piston cylinder, that is your system. Anything else outside would be considered as a surrounding. So here, under this note, I mentioned that turbine extract energy from the working fluid, because consider a fluid, right? It is the fluid that does work on turbine blade. So basically turbine, what it does, it extracts energy from the working fluid. But for pump or, compressor, they, add, but basically, they increase the mechanical energy of the fluid by increasing, for example, pressure of the fluid. What pump does, it increases the pressure of the fluid. So pressure of the fluid at the outlet of the pump is higher than compared to the inlet. So basically what it does, it adds energy to the fluid, but for turbine, it extracts energy from the fluid. We get into details later on. So if you look, for example, the turbine and how it works, here is a turbine. There is inlet and outlet for the turbine. Here is inflow. Here is outflow, right? And there is a generator, right? And the turbine extracts energy from the fluid, and it is the fluid that does work on the turbine blades. And the output of the turbine is shaft work or mechanical power. That is the output of the turbine, which goes as an input to the generator. And the generator use that as an input and produces electricity or electrical power. And that is the output of the generator. Sometimes we pack these two together and just look at it as a package. So the output would be electrical power. And basically, if you look at this working fluid, you see that at the outlet of the turbine, the mechanical energy of the fluid is less than mechanical energy of the fluid in the inlet. For pump, however, there is a motor that uses electrical power as the input, and the motor converts that electrical power to shaft work or shaft power. And there is fluid inflow and outflow of the fluid. There is inlet and outlet, and basically the pump use this shaft work or mechanical power as the input and transfer that. Not all of that, because the efficiency is not 100%, but fraction of it will be transferred to working fluid. So if you compare the mechanical energy of the fluid at the outlet of the pump is higher than mechanical energy at the inlet of the pump. Is there any question, guys?
Yeah, just like one thing. So for the turbine, so because I really can like imagine. I know for turbine, I know it kind of looks like it sucks like energy, and then convert it to like to do work. And I was just wondering like how does it work for a generator? Like because I see there's an outflow and then there's like a direction going for the generator. How does that work?
For the generator, I didn't understand exactly your question, but I'm thinking you're asking about the generator, right? How it works. See,
Yes,
for
yes.
generator, there is input and output, right? So the input to the generator is basically the shaft power, the shaft work, which is the output of the turbine, right? And then the generator converts that shaft work to the electrical power, which is the output of the whole package. So basically what the whole thing does, the turbine combination with the generator, it extracts the energy, the mechanical energy of this fluid, and then, at the end, it will be converted to electrical power. So we get into more detail as we get to efficiency and stuff for turbine and for the pump. This is just to mention that, sometimes the work will be added to the system. Sometimes it will be, the work will be subtracted. It will be transferred out of the system. Sometimes it's into the system. Sometimes it's out of the system. By the way, you have to be careful because sometimes you are writing energy equation for the fluid, and it's different than when you consider the device. So later you see, specifically if you take fluid mechanics, I'm talking about Emitted 390, you would see we apply energy equation to the fluid, and if there is pump involved along the way of the fluid, then the power of the pump will be added to the energy of the fluid when fluid passes through the pump. Okay, so the power of the pump will be added. But for turbine, because it is the turbine that extract the energy from working fluid, when you are applying energy equation to fluid passing through a turbine, the power of the turbine will be subtracted from fluid, because you are applying energy equation to the working fluid. But here, when you are focusing on turbine, we'd say that a combination of turbine and generator, it produces work. Now you are looking at the device, it produces work, but when you're looking at this package, pump and motor, they consume some work, and that work or energy will be transferred to fluid by increasing the pressure of the fluid, for example. All right, but at the for the turbine, if you compare the mechanical energy of the fluid at the outlet of the turbine, you will see that mechanical energy of the fluid, they will be decreased the mechanical energy of the fluid. I'm going to get into more details later on. What is this slide doing here? Oh, you know what? I want to explain. Okay. I think previously I explained that. Here under this note, I wanted to explain that work and heat, because we are talking about energy transfer into the system, energy transfer out of the system. This system can be pump and water inside it, right? So it can be turbine, it can be pump, it can be anything, but it can be heat exchanger. We already talked about heat transfer into an auto, and now we are talking about work transfer into an auto. Here it wants to explain that work and heat, they are not path function. So they don't depend on the process. They don't depend on the path. Sorry. They are path function. They are not point function. I misspoke. See, here there are, this is the diagram. It can be any type of diagram. So this is PV. The y-axis can show pressure, or it can show temperature, and the x-axis, it can show, in this case, it shows a specific volume. It can also show enthalpy or, internal energy. Anyhow, whatever this diagram is, in this case, PV diagram, for example, the substance is at the state one. For example, consider, a piston cylinder. All right. So it is at the state one with P1 and V1, P1, value of P1 and V1. And then there is a process A, that takes the system, this piston cylinder, from a state one to a state two with value of pressure, let's say P2, and temperature T2, and a specific volume, Nu2. And as you see, in this case, that's expansion, because as you go from a piston cylinder, for example, it can be any system. Let's consider a piston cylinder. It goes from a state one to a state two. You see that pressure drops, goes from P1 to P2. And, a specific volume increases from Nu1 to Nu2. The trend of a specific volume and volume is the same. So it's expansion, and then it goes from a state 2 to a state 1 through process B. Process B goes from, a state 2 to a state 1, and, it is a cycle in this case, but it's not about, I just wanted to mention that, it's not like when the state, the value of work, you cannot assign, work and heat to a state. It's not like, okay, you're at a state one, and value of work is W1 here, and value of heat is Q1, and you're at the state two, value of work is W2 and Q2. So when it goes from a state one to a state two, W2 minus W1 is the work done. No, it's not like that. It's not point function. You cannot assign value to work and heat at the state, pressure, temperature, the total energy of the system, they are point functions. So once you know the state, you know the pressure P1, the temperature T1, the total energy of the system, E1, but not work done. So work and heat depends on, the path, depends on the process. They are not point function. Keep that in mind. It's very helpful. And then we want to talk about different type of work that may be done or, may be added or subtracted from a system. One of the work is, by the way, we know that work per unit of time, W dot, which is W divided by delta T time interval, that is power. In a SI system, it's kilojoule per second, and joule per second is called watt. So it's kilowatt, right? It's either joule per sec, which is watt, or kilojoule per sec, which is kilowatt. So work per unit of time, that is power. And work per unit of mass, we denote it with lowercase w, which is capital W divided by M. So work per unit of time, that is W dot, which is called power, but work per unit of mass, which is capital W divided by M, mass of the system, that is lowercase w, which is work per unit of mass, right? And there can be electrical work involved. So here is the voltage, here is R is resistance, I is current, and the electrical power, W dot for power, E for electrical. Electrical power can be calculated using this formula, VI, or RI square or V square over R. V is the voltage, R is resistance, and I is current. And, in order to calculate the total work, power is basically work per unit of time. And if power is constant, then you can multiply power by time interval, and that gives you work, right? So work is power time delta T, and here is delta T, and power is just VI, so VI delta T. But that is when power is constant over the time interval delta T. So VI is constant, but if they are function of time, V is function of time, voltage, and I is function of time, then you have to divide this time interval to differential. So time interval from T1 to T2, you have to divide it to dt, 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 and over dt, calculate differential work, which is VI dt, and then take integral going from 1 to 2, and that is the total work. All right. Is there any question so far? All right. Then we want to talk about, mechanical work. So we know how we calculate work. If F is constant over displacement S, if the body displaces by distance S, then work can be calculated Fs. By the way, it's not that simple. We learn in dynamics that because a force is a vector and displacement is a vector, right? So basically it's dot product between F and S. So if F dot product S, which is basically dot product, we know from, if you take ME501A, I used to teach that course. It's a beautiful course. We talk about this operator that we use in engineering, along with, differential equation and stuff, all the tools that powerful mathematical tools that we need in different courses, like thermodynamics, heat transfer, fluid mechanics, fluid dynamics. But one of those is this operator dot product. If there are two vectors and dot product between A is a vector, B is a vector, A dot product B is magnitude of A times magnitude of B times cosine of theta, and theta is angle between vector A and B. And work is basically dot product between vector F and vector S, which is displacement, and vector F, which is the force. But if angle between these two is 0, so they are both parallel in the same direction. So angle between two, for example, they are from left to right. Angle between these two is 0, so cosine of 0 is 1, so we come up with Fs. But this is not a dynamics course. I just want to mention that for you to know as an extra information. But if force is not constant along the way, we can use this formula if displacement is S and force is F, and F is constant along the way. If F is function of S itself, so magnitude of force depends on location, then you have to divide the displacement at to dl, differential displacement and over ds. Calculate work, which is FDS. We assume that F is constant over ds. And then add them up. Continuous summation is integral. Take integral from location 1 to location 2 from FDS, all right? And so we know that pump uses mechanical work, all right? Because there is a motor, and motor uses electricity as input, and the output of the motor would be shaft work, which is mechanical work, and that goes as input to the pump, right? And pump adds that energy, a fraction of that energy depends on the efficiency of the pump to fluid, and the mechanical energy of the fluid increases. So at the outlet of the pump, mechanical energy of the fluid is higher than compared to the inlet because pump increases the energy, the pressure, and by that the mechanical energy of the fluid increases. For turbine, however, it produces mechanical work by extracting energy from working fluid. So the fluid goes from inlet to the outlet and works on turbine blade. So turbine basically extracts energy from working fluid, and it is the fluid that works on turbine. And that energy will be converted to, shaft work, which is the output of the turbine, which goes as an input to generator, and generator produces energy. So in form of electricity. And if you compare the mechanical energy of the fluid at the outlet of the turbine and compare it with the inlet, you see that decreases. Later we will see how we can calculate that. Now we get to another type of work, which is piston work. So if there is piston cylinder, we want to see how we can calculate the boundary work or the piston work. So here in this example, sorry guys, we assume that this is piston cylinder, and we are at a state 1, right? And I also show it at the same time in this diagram, which is PV diagram, pressure of, let's say, air inside, and volume or specific volume inside. So at the state 1, we are here with, V1 and with P1. Then if you go from state 1 to state 2, then here pressure P1, say pressure P1, volume or specific volume V1, and then there will be compression as you go from 1 to 2, as you see, as you go this way from 1 to 2, P2 is larger than P1, so pressure increases, and V2, which is this, is less than V1, so it is compression, pressure increases. Pressure increases, volume decreases as you go from 1 to 2. And then you want to calculate the work done. The pressure is not constant all along. If the pressure was constant, you say, okay, you know what? Pressure is force per unit of area. I am going to multiply pressure by the area of the piston. That gives me the force. And if force is constant, PA times this distance, that is work. But the thing is, pressure is not constant, can be the function of displacement. So pressure is not constant all along. So you multiply pressure by the area, and that is force, right? Because pressure is force per unit of area. Multiply pressure by the area, that is force. And then, when you want to calculate work, you divide this distance by, DL, and PA times, DL. That is, differential work. That is differential work. And then you take integral, which means you add them up. It's a continuous summation. Integral is like continuous summation. You take that from 1 to 2. So it's PA DL, right? And you can pack these two together, and rearrange this. And ADL, area of the piston, times DL is D volume, differential volume. So it's P differential volume from 1 to 2. Okay, so A is area of the piston, force is PA, and that's that. Is there any question, guys? All right, so that formula you can use in order to calculate the bonding work. Keep that in mind. PD volume. I use this notation for the volume. All right, so it's pressure times the volume going from 1 to 2. Later, we are going to get into details. And as we get to, chapter 4, and we want to apply first law to closed system like piston cylinder, we are going to, I'm going to break it down into different cases and calculate the bungee work under different conditions. This is just the introduction. And there is shaft work, so if there is a shaft involved, for example, there is piston cylinder and there's a fan inside it, you have to consider that work too. So work can be electrical work, it can be shaft work, it can be bungee work that we just talked about in previous slide. And now the shaft work. How do you calculate the shaft? The work is always a force times displacement, F times S, right? And we're going to substitute for F, and we're going to substitute for S. And, that's way we can calculate the work, shaft work. We know F, if you consider the cross-sectional area of this shaft, a force F acts on it, F times R, that is a torque of shaft. And so in terms of torque, you can write F is torque divided by radius of the shaft, right? So we know FR is torque. So torque divided by R is F, right? So we can substitute for F using this equation number 3. So this is equation number 1, which is pure definition of work. This is equation number 3 that we can substitute and write F in terms of torque and R. And now S. S is traveled distance. So if shaft rotates, this is the total number of revolution. So the total number of revolution is N, and each revolution, by each revolution, it travels 2 pi R, right? So 2 pi R times S, that is the distance, travel distance. So that is equation number 2. We are going to substitute S using equation number 2, and we're going to substitute F using equation number 3 and plug everything in equation number 1, right? So if you do that, W, just copy paste. For F, we have T over R, and for S, we have 2 pi R and R cancel out. So we will have 2 pi NT, right? And in order to calculate the power of the shaft, we have to divide both sides by delta T, the time interval over which it traveled this distance. So our left side gives you power, shaft power, if you divide it by time interval. If you divide right side by time interval, 2 pi just copy paste, T just copy paste, and the number of revolution you divide it by delta T time interval, that gives you revolution per unit of time, which is N dots, and that is also called frequency, right? Frequency of rotation. Please also review this example 2.7, and that is on page 67 in my edition. It might be 1 page difference, but around page 67, example 2.7. That is the example. I'm not referring to selected problems from the end of the chapter, just example and the solution within the chapter, example number 7. So here is how you can calculate power of the shaft. Because if there is a shaft involved, like a fan inside the piston cylinder, and you have the torque of the shaft, you can use this formula to get the power of the shaft, because part of E in or E out, if there is shaft involved, part of E in would be power, because it's E dot. In energy balance equation, it's W dot, right? And W dot is power. That can be, electrical power. It can be shaft power like this one. It can be, so you have to include that into energy balance equation. Now, we want to talk about a springboard. So that is different type of work. And, for a spring, if you pull a spring, you create deformation in the spring, and any deformation creates a resistance to deformation. So it creates opposite force that is equal to this force that you use to pull it, but in opposite direction to reverse this deformation, right? So in order to pull it, you have to exert this force, but this force is not constant. It depends on deformation. So basically, it's a function of x. So if here is the rest position, then when you pull it, F, the force that you have to exert is function of x itself. And actually, the way it obeys x, the function is kx. So this force is kx. K is a spring constant. It depends on the spring. It's given. And x is just displacement, right? Deformation you create. And because of that, if you create this deformation, if you pull it by distance x, and you want to calculate work done between 1 and 2, because force is not constant along the way. It's not like you can multiply F by X and say, okay, here we are. You have to divide this distance by dx, and over dx calculate the work, which is F as a function of X, which is kx dx, right? And that is the work over distance X. Then add them up, differential work, right? So you take integral going from 1 to 2 from differential work, which is fx dx, and fx itself is kx dx. And you can take k out, it's constant, and integral of x dx is half of x squared. Then you apply upper bound and lower bound, so it becomes half of k squared, x2x squared minus x1 x squared. That's how you calculate work done by this spring. And if you are raising or accelerating a body, raising the elevation of the body or accelerate the body, there will be a work involved. Basically, if you accelerate the body, the kinetic energy will increase, and work needed to accelerate the body, which is the same as change of kinetic energy of the body. So the work you do to accelerate the body will increase the kinetic energy of the body. So the work you do is the same as increase of kinetic energy of the body, which can be calculated by half of m. M is mass of the body, v2 squared minus v1 squared, because kinetic energy is half of mv squared. So if it goes from velocity v1 and accelerated to v2, the work you have done is the same as increase of kinetic energy of the body, which is half of m v2 squared minus v1 squared. And then if you raise the elevation of the body, work needed to raise the elevation of the body is the same as change in potential energy of the body. So if elevation changes by delta z, we go from z1 to z2, then the work you have done to change the elevation of the body is the same as change in potential energy of the body, which is mg delta z. So that is how you calculate that. So we are done with this lecture. I'm going to stop here. And if you want to see me, you can meet with me after the class. If you have any question, you can ask me. So please start studying the slideshow. We haven't got to the, points that we will soon to get to the point that we can solve lots of, problems as we get to. Right now, I'm trying to explain, first law. Starting from, first law is the same as energy balance equation, an energy balance equation based on conservation of energy. So they start from this simple principle, conservation of energy, and then apply the general form of energy balance equation and work on the components, E in minus E out is delta E of the system. I try to explain what delta E is, changing kinetic energy, changing potential energy, changing internal energy of the system, and try to break down E in and E out, that is energy transfer into and out of the system respective in form of heat in and out, transfer in and transfer out of the system, work transfer in out of the system, and if the system is open, that is, energy transferred by mass, into or out of the system. And then the next step would be, we are going to introduce different devices, as I said, closed system, like piston cylinder, open systems, like heat exchanger, and all of those engineering devices, and try to tailor the first law for each and have lots of examples. So I already sent you the slideshow. So you have all the tools you need. So I start studying reviewing. Very soon we get to the point that we can, do some examples, some practice examples. And it's, during the lecture, we are going to do lots of examples that I ask you later on to redo them in addition to selected problems from the chapter. Is there any question you may have for me? Any question whatsoever?
Yeah, Professor, in the email that you sent us on Saturday, you sent us chapter 2 problems and chapter 1 solutions.
Oh, really? Oh, okay. Thank you for letting me know. So that is chapter. Oh, okay. So I'm gonna send you the one more time the selected problems.
So you
from
sent us chapter
Mm.
2 problems. So you would need to send us the chapter 1 problems and the chapter 2 solution.
I will. Thank you for letting me know.
Thank you.
So I'm gonna fix that. Thank you for bringing it to my attention. All righty. So any other question, guys?
That'll be it. Thank you.
Thank you. So have a great weekend and see you guys next week. Is there anyone who wants to see me after the class? No one? All right. So have a great weekend, guys.
Have a good weekend, Professor.
Thank you.
Professor. Have a good weekend.
Professor.
Thank you as well.
Have a good weekend, Professor. Thank you.
Thank you too.